Well, hello and welcome, class. In class previously this week, we took a kinematics quiz, and a lot of us didn't do so well. To be fair, that was somewhat expected. We've rushed through this stuff really fast, so now we get to take some time, slow it down. We're going to go through problem by problem how to solve these and what we're thinking while we're solving them. If you want to skip around and go to the problems you don't understand, you're welcome to do that, or sit back, relax, and watch the whole video. So this is Kinematics Quiz Explained. Let's jump right into this. Number 1 says the change of distance per unit time without reference to a particular direction is called. What would that be called? We've got displacement, speed, velocity, acceleration, and position. So change of distance here per unit time. But it says without particular reference to direction, so no direction here. In the notes we talked about two different types of quantities. There were scalar quantities and there were vector quantities. And scalar quantities, those were the ones that had magnitude only, so those just had a number associated with them. Vector quantities, these ones had some type of number, there was magnitude, and they had direction. So we know if this has no particular reference to direction that all of the vector quantities aren't going to be in there. So displacement's a vector quantity, velocity, and acceleration. Those are all vector quantities. They have to have direction. So change of distance per unit time. Distance per unit time, that's going to be speed. That's our definition of speed there. So distance per unit time, that's speed. Good. Let's move on to question 2. It says a woman drives at 30 miles per hour. No, I'm sorry. Drives 30 miles at an average speed of 60 miles per hour. Then she drives another 30 miles at an average speed of 30 miles per hour. What is her average speed over the full 60 miles? Now, a lot of us, this is what we do. We get ahead of ourselves and we think, I'll take 60 miles an hour, I'll take 30 miles per hour, I'll add those up and divide by 2 because that's how I find my average. Let's draw a little picture here that helps us. For this first 30 miles, this woman driving, I like to think of this as my grandma, we'll call her Gram. Gram drives these first 30 miles at 60 miles per hour. Then the next 30 miles, Gram drives at 30 miles per hour. And if we were just to add those up and take the average of the two, what's wrong with that? Is Gram driving for the same amount of time for both of these? She's driving 60 miles an hour for 30 miles. Is that going to take the same amount of time as if she were driving 30 miles an hour for 30 miles? And the answer there is no. In this one here, this is only going to take her a half an hour. In this case here, if she can go 30 miles per hour, and she's going 30 miles, that'll take an hour. So that total time is going to take her 1.5 hours. So if we're finding average speed, the average speed, and we just saw this above, I'm going to scroll up, average speed is distance per unit time here. Distance per unit time. So average speed is going to be distance over time. We've got our total time. How far did Gram travel? 30 miles and then 30 miles, so total is 60 miles. And we can divide this here, 60 divided by 1.5, that's 40, and our units are going to be miles per hour. Typically we would write, if this were meters per second, we'd write meters per second. But miles per hour, we have notation that we like to use, so mph there. So the answer to this one is B, right there, 40 miles per hour. Alright, let's take a look at number 3. Cheetah can run at speed of 20 meters per second. That's pretty fast. It can go 20 meters in 1 second, while the gazelle can only run at a velocity of 5.5 meters per second. So gazelle right here at 5.5 meters per second, the cheetah's at 20 meters per second. The gazelle starts out 45 meters in front of the cheetah. So how much time will it take for the cheetah to catch the gazelle? That's what we want to find here. Ultimately, we're doing some problem solving. There's going to need to be some math that goes on. But it helps to look at this problem graphically first, okay? It happens a lot in physics. There's math, there's graphing, reading. All of these things can be useful in visualizing a problem. So let's graph this. Let's imagine we have a position time graph here. That's an awful line. Let's imagine we have a position time graph here. And we're going to do position on the dependent axis. The units there are meters. Time is down here on the independent axis. This is just good practice for us too, to review some of the other stuff that we've learned. So remember, this is a position time graph. Graphs your position at any moment in time. The slope, very important here, the slope of a position time graph is your velocity. So let's take a look at the gazelle first. The gazelle starts out, like we said, 45 meters ahead of the cheetah. So somewhere up here at 45 meters, the gazelle will start. And the gazelle has a velocity of 5.5 meters per second. That means the slope of this line is 5.5 meters per second. Good. The cheetah runs at a velocity of 20 meters per second. So the cheetah starts down here at 0 meters, and the cheetah runs a lot faster than the gazelle. So the cheetah is going to start here. It's going to run at some velocity like this, much steeper slope, because 20 meters per second is much faster than 5.5 meters per second. Notice here, right here, they intersect. Okay, so there's an intersection, and we want to figure out what time, if we were to draw a line straight down here, what time is the cheetah and the gazelle at the same position. So for what position are they at the same place at the same time? That's what we're trying to figure out. The reason graphing this helps us visualize is because typically, if you're in physics by now, you've done some algebra, you know that these are linear relationships, and you know how to write a linear equation. Here's what I don't want you to do. I don't want you to write anything that says y equals mx plus b. Even though that's the formula for a linear equation, we're not dealing with y's and x's here. We're dealing with position and time. In physics, this is where math makes sense, and these variables have real meaning. They're not just numbers, they're not just letters, okay? So let's do each of these. Let's do the cheetah first. So we've got a cheetah here. The position of the cheetah, that's on the independent axis. The position of the cheetah is going to be equal to the slope of that line, which is your velocity, times time. Now I'm going to rewrite this actually. The position of the cheetah is going to be equal to that slope, which is 20 meters per second, times time. And then this plus b part, that is your vertical intercept here, vertical axis intercept. The cheetah's is at 0, so I'm not going to write that. Okay. Now we can do the gazelle. The position of the gazelle is going to be equal to the slope, which is 5.5 t. And then there is a vertical axis intercept there. Remember, the cheetah started out 45 meters ahead, so the position of the cheetah 45 meters ahead. So at time equals 0, the cheetah hasn't moved yet, but it is 45 meters ahead. Now remember, what are we even trying to find here? How much time will it take for the cheetah to catch the gazelle? Or at what time will the cheetah and the gazelle be at the same position? This is going to look silly at first, but this is so important for you to see. If the gazelle and the cheetah are at the same place at the same time, if the cheetah's caught the gazelle, that means that the cheetah's position, x, we're using x for position, the cheetah's position is going to be the same as the gazelle's position. Whoa, revolutionary, I know. X equals x. Position of the gazelle is the same as the position of the cheetah. Now we can substitute in these two equations, right? So if this is the cheetah's position, we've got 20t, and that's going to be equal to the gazelle's position, which we also know is equal to 5.5t plus 45. From here you could do some algebra, and you can subtract this subtract this 5.5 from each side, minus 5.5t. This ends up being 14.5t equals 45, and divide by 14.5 on both sides, and you would solve for t. I'm going to move this over here, that t is equal to about 3.1 seconds. I always have the units on there, circle my answer. So answer here is B, 3.1 seconds. That means at 3.1 seconds, the cheetah and the gazelle will be at the same position, okay? Or the cheetah's caught the gazelle. Good work. All right, let's move on to number 4. How long must an acceleration of 2.5 meters per second squared, that's my acceleration there, act to change the velocity of a 2 kilogram object by 3 meters per second? So this is going to be my change in velocity. Now, part of physics when you're reading these problems, especially for an AP physics, you got to think to yourself, what type of question is this? If it's talking about acceleration, could be kinematics, could be dynamics, could be rotation, could be a whole lot of things. Right now we've only been doing kinematics questions, so you know it's kinematics. We haven't even talked about mass, so you know that's not relevant. But part of when you're taking the AP test, you really got to think to yourself, what's relevant information to what I'm trying to solve, what's not relevant, what's irrelevant. So we know the mass isn't relevant for now. What we're really asking is how long must acceleration of 2.5 meters per second squared act on an object to change its velocity by 3 meters per second. Something you should think about here. You want to plug this into an equation right away, but you don't need to. If you think about the definition of acceleration, what that means, well, let's just play around with it. So acceleration is how velocity changes for every second in time. So if you're trying to change the velocity by 3 meters per second, this acceleration tells us that every second you're changing the velocity by 2.5 meters per second. Obviously this is going to take longer than a second, because in 1 second you're only going to change it 2.5 meters per second. Okay, all of our answers except A are greater than that. So let's think a little bit more. Acceleration is the change in velocity per unit time. So if we have an acceleration of 2.5 meters per second squared, or meters per second is a good way to think about that, and we're changing our velocity by 3 meters per second, how much time is that going to take? This is actually a little tough. You kind of got to multiply on time by both sides, then divide by 2.5. A lot of people mess this simple algebra up. But what you'll see here is how much time that'll take. Units all cancel out, so you end up with just seconds. And you find that this takes 1.2 seconds right there. So our answer again is B. It takes 1.2 seconds for an object with an acceleration of 2.5 meters per second to change by 3 meters per second. Good. Let's move on to 5. Number 5. This is our first real kinematics question, at least as far as acceleration goes. It's our first real acceleration problem where we get to dive into those equations, right? A car starts from rest and uniformly accelerates to a final speed of 20 meters per second in a time of 15 seconds. How far does the car travel during this time? With these problems, a lot of times what you need to think of is what type of problem is it? Obviously talking about acceleration, this could be a kinematics problem. And then we need to think, okay, what is it I'm really trying to find? How far? Okay, this is going to be that your displacement. How far have I traveled during that time? One method of solving this is to think about what is it that I know, what is it that I'm trying to know, and then do I have any conceptual ideas or equations that'll help me get there? So with these equations, at least to start out, you should probably just write out all of the variables that there are for a kinematics acceleration question. Figure out what it is you know and what you want to know. We already said we're trying to figure out how far the object travels. So we're looking for this right here. I'm going to circle that. That's our ultimate goal. Okay. And then we can go through. Do we know what the starting velocity is? It says a car starts from rest. From rest means it's going to start with a velocity of 0 meters per second. I'm using meters per second instead of miles per hour or kilometers an hour or feet per second because we want to keep the units consistent. From rest is a tricky one. You're looking for numbers, they're using words. Make sure you recognize anytime it says from rest or stopped. keep going. Final velocity. What velocity does it reach? Accelerates to a final speed of 20 meters per second. So that final velocity, 20 meters per second. Acceleration, we don't know that yet. I don't see that anywhere up here. Time. How much time does the whole thing take? Whole thing took 15 seconds in time. Good. So we're trying to solve for position, and all of you should have your equations out. Okay, I want you to get really comfortable with the AP Physics 1 equation sheet because that's what you'll be allowed to use on the test. Eventually you'll have most of these committed to memory, but in the meantime you need to look at them over and over again. Now I know that if I'm trying to solve for position, I can't really solve for any of these variables unless I know acceleration. So I need to find acceleration first before I can find position. So we'll find position second, or displacement second. So I know from experience and from looking at these equations that in order for me to find acceleration, if I don't know displacement, I have to use what I call the first equation. That's the first one listed there. Looks like this. I can plug in these numbers. This is 0 meters per second. I'm writing in the 0 for now, just so you get used to seeing it. Some people wonder, hey, where'd it go? Eventually, if it's a 0, probably don't have to write it in. Plus the acceleration, which is what we're trying to find, and the time was 15 seconds. Subtract 0 on both sides, do 20 meters per second divided by 15 seconds, and we find that the acceleration here, 1.33 meters per second per second. I rounded here. This is actually 1.33 repeating. We'll talk more about rounding and significant figures in class. Okay, so we know acceleration, good for us. Let us find position now. Two equations left that we can find position with. I'm going to choose the easier of the two because it's already solved for position for me. So we're solving for the final position or the displacement. Initial velocity is 0. Our time is 15. Put my units in here if I wanted to check and see if units worked out. Acceleration we just found 1.33 meters per second and time is 15 seconds, and we're squaring that time. Okay, 0 times 15 just goes to 0, so I'm going to cross that out. Half times 1.33 times 15 squared, that is about, and I'm going to round here, reasonably round, 100, nope, I'm going to round here, this is about 150 meters. Multiple choice is nice because you get to check and see if your answer's up there. Letter A, 150 meters. Good work, team. Let's move on to number 6. Number 6 is very similar in that you're given some velocities, you're given displacements or times. It's an acceleration problem. We're in kinematics. So it says a box falls to the ground from a delivery truck traveling at 30 meters per second. After hitting the road, it slides 45 meters to a rest. How long does it take the box to come to a rest? And the last problem, I started out by listing the things I knew and what I was looking for. I'm going to do that here too, but I might draw a picture first if I really wanted to. So maybe this is at the beginning. This box hits the ground, and the box is traveling at 30 meters per second. And then it travels a big old distance here of 45 meters. And when the box gets to 45 meters over here, moving a window on me. When the box gets to 45 meters over here, it has a speed of 0 meters per second. Okay, it might help you a little bit just to see that. I knew that it ended up with a velocity of 0 because it says that it comes to a rest. Tricky phrase there. Let's list what we know, what we don't know. Alright, starting out, velocity is 30 meters per second, technically to the right, or to the positive in my picture. Final velocity, 0 meters per second. Remember, it comes to a rest. Acceleration, we don't know that yet. Final position is 45 meters away from where it started. And the time it takes, we don't know that either. That's what we're looking for. How long does it take? That means how much time passed for that to come to a stop. Ultimately, we're solving for time. This is another one of those cases where we don't know acceleration. If you're going to find any of these other variables, you need to know acceleration first, and then we'll find time second. So if we don't know time, we can't use it in any of those first three equations, so we're going to have to use a different one. Here's another equation that we haven't seen yet in this quiz. Final velocity is 0 meters per second. The initial velocity, which I shouldn't be writing a v there, the initial velocity is 30 meters per second plus 2. We're solving for acceleration. 2 multiplied by the acceleration times that displacement of 45. So 30 squared here, that is 900. We're going to subtract that over. So you get negative 900, and we've squared these units as well, is equal to 2 times 45, which is 90. And those are going to be meters. And we're multiplying that whole thing by acceleration. Divide by 90 on both sides, and we find that the acceleration is negative 10 meters per second. Okay, or meters per second squared. So our answer here, oh, that's not what we're looking for. We need acceleration, that's good, but we're actually solving for time. I lost track of what we were looking for. We know acceleration. Now let's solve for time. I'm going to use this equation because I don't want to use the quadratic formula to solve for time in the second equation. Final velocity is 0 meters per second. The initial velocity is 30 meters per second. We just solved for our acceleration, which is negative 10, and that's meters per second squared. Got to fit this in. Multiplying that by time. Subtract 30 over. Divide by negative 10. That means you get a negative 30 meters per second on this side. Divide by negative 10 meters per second squared. If you wanted to check out all these units, you should get the correct units for time, which are seconds. This ends up being 3 seconds for your time. Time should always be positive. So the correct answer for number 6 is letter D. Time is 3 seconds. Good work. Checking out number 7, it says a car starting from rest. Ooh, there's that tricky starting from rest again. Ooh, hey-oh, don't wanna. Starting from rest again. Accelerates at 0.8 meters per second. So there's your acceleration. Sometimes it helps to put the variable next to it. For a time of 10 seconds. Then continues at a constant velocity. Okay, which of the following is true? The car at 20 seconds. Little tough. We need to visualize what's going on here. This is more complicated than being just an acceleration problem. When you're looking at kinematics problems, you're thinking to yourself, okay, is this an acceleration problem or a constant velocity problem? Constant velocity means your velocity stays the same over time. An acceleration problem means that your velocity is speeding up over time. So we need to figure out which it is. In this case, it's both. It can be both at the same time, but it starts out as acceleration and then becomes constant velocity. So if I was to start right here at time is 0 and go for 10 seconds. I'm not even going to draw that line there. Go for 10 seconds. So this is at time equals 10 seconds. I'm accelerating. So I'd start here. Switch colors for you. So I start right here. If I'm accelerating, I'm going slow. I'm not going to cover that much distance at first. Then it's going to get bigger. Then it's going to get bigger. And it's going to get really big. That's because I'm speeding up as I go. If I'm going faster, I'm going to cover more I'm going to cover more ground for every second. So technically, if each second represented a dot here, I'd have 10 of them. But we're just drawing this to wrap our heads around it. For the next 10 seconds, so if I was to go over here again, for the next 10 seconds at t equals 20 seconds, I would continue going at the same speed that I was right here. Okay, good. So what are we trying to find here? We're trying to figure out which of these statements is true. We want to figure out what's its velocity at 20 seconds and how far has it traveled at those 20 seconds. And we realize that part of this problem is an acceleration problem. Part of this problem is a constant velocity problem. So we got to be able to break that apart. Let's look at the acceleration problem first. I want to figure out at t equals 10 seconds, what is the velocity and how far have we traveled. So I'm going to do that over here. Let's just do from 0 to 10 seconds. Okay, this is a constant acceleration part. Let's write down our variables. Let's figure out what we know, what we're trying to know. We already know that this is what we want to find right here for the first 10 seconds. Starts out from rest, 0 meters per second. We're looking for this. Acceleration, 0.80 meters per second per second. We're trying to find this. And we know at t equals, this is from 0 to 10 seconds. So we're looking for it at 10 seconds. All right, finding position and velocity. What's my easiest way to do this? For velocity, first equation. How do I know that? How do I know which equation to use? All of these kinematic equations, these first three, they've got 4 variables, and if you don't know one of them, or if you want to know one of them, you need to know the other 3. So I look at this equation and I say to myself, I'm looking for final velocity. Do I know these other 3? Yes. So this is initial velocity of 0 meters per second, acceleration 0.80 meters per second squared times 10 seconds. So your velocity here is going to be 8 meters per second. Good. That's the velocity right here. I'm going to maybe erase out. I'm going to leave that there because I don't know how to change it. Velocity is 8 meters per second. What is your displacement? Displacement here. Let's use this equation. It's already solved for displacement for us. The initial velocity is 0, right? So this 0 times 10 seconds, that's going to go away. So you get 1/2 your acceleration, 0.80 meters per second squared, and your time is 10 seconds. And you're squaring that. 10 squared is 100. 100 times 0.8 is going to give us 80. Half of that is 40 meters. So that's how far you've traveled in this distance here, 40 meters. And that velocity, that was 8 meters per second. Halfway there, for the next 10 seconds, we know that it goes at a constant velocity. So if it's at 8 meters per second at t equals 10 seconds and continues at a constant velocity, at the end here, it's still going to be at 8 meters per second. That's what constant velocity means. It means it's not changing. It has an acceleration of 0. Good. Well, that's easy. Easy enough anyway. Let's figure out how far it travels during this time, and then we'll be able to add these two up and figure out how far it traveled overall. Something interesting here. If you were to count this as an acceleration problem, I just mentioned the acceleration is 0. So if you were to consider this as an acceleration problem, the acceleration here is 0 because it has a constant velocity during the whole time. There's no change in velocity. If this acceleration is 0, we get to ignore this whole part. And the initial velocity was 8 meters per second, and it stays that the whole time. So this initial velocity is just going to be constant. So our position is going to be our velocity, which is 8 meters per second, times how long we're looking at, 10 seconds. So during this second phase, 10 to 20 seconds, this guy's going to travel 80 meters. So 40 meters in the first 10 seconds, 80 meters in the second. That means he's going to travel a total of 120 meters because 40 meters plus 80 meters is 120 meters. Let's see if we have enough information now to figure this out. We said at the end it's going to be going 8 meters per second. So we've got 8 meters per second here. And then it said total he'll have traveled 120 meters right here. Looks like C is going to be our answer. Okay, 8 meters per second at the end there, velocity, and traveled 120 meters. Tough problem. That's a tough problem. 8. What is the average speed of the ball between 3 and 4 seconds? So we're given a picture here, and this picture is actually a motion map in some sense. It tells you the position at each time, but it's kind of drawn out in a picture for us. And it says, what is that average speed for the ball between 3 and 4 seconds? Alright, so we do have an equation here for average speed. Speed is distance over time. How far are we traveling? We're looking at 3 to 4 seconds. We travel from 9 centimeters to 16 centimeters. So that is 7 centimeters that we're traveling. And how long is the time that we're traveling here? From 3 to 4 seconds, that's just 1 second. So you're going to have 7 centimeters per second. So we're looking at B, 7 centimeters per second. Okay. Problem number 9 here, we're looking at which of the following is closest to the acceleration of the ball. The previous problem was asking us about speed. That's similar to velocity. There's no change in velocity during that time technically, but really the ball is accelerating here. Every second it's going further and further and further. We want to figure out what is that acceleration. How can we do this? Let's look at the first instant here where we've got at 0 seconds, it's at rest, it's at 0 centimeters. And then over here at the end, 5 seconds later, it is at a position of 25 centimeters. Okay. Let's use this to solve for acceleration. Let's see if we can figure this out. We know that it's accelerating, so we're going to always write this. You're going to love writing this. I wish there was a stamp for it so you didn't have to write it every time, but it's good for you. It builds character. Starts out at rest, 0 meters per second. We don't know that final velocity. It's at least not given to us. We could maybe find it. Acceleration, this is what we're looking for, so I'm going to circle that. The position at the end there, 25 meters per second, so that's how far it traveled from 0 to 25. And the time duration is 5 seconds. We know with our kinematic equations, those first 3 on the sheet, that if you know any 3 variables, you can solve for another 1. So let's figure out which equation here is going to help us solve for this. My thought is this one here, right there. So the final position is 25 centimeters. The initial velocity is just 0. Time is 5 seconds. This whole thing is going to go to 0 because 0 times 5 is 0. Plus 1/2. I want to find acceleration and a time of 5 seconds. And we're squaring those 5 seconds. So you get 25 equals 1/2 times a times 5 squared. 5 squared is 25. 25 times a half is 12.5. 25 divided by 12.5, you end up with an acceleration of 2 centimeters per second. Very nice. Looks like C is our answer there. Last problem. Okay. Last problem's it's a tough one. Got a body moving in the positive x direction, passes the origin at time equals 0. Between time equals 0 and time equals 1 second, so that's the first second, the body's moving at a constant speed of 24 meters per second. Okay, that's your constant speed during that time. At time equals 1 second, the body is then given a constant acceleration of 6 meters per second squared. That's your acceleration in the negative direction. This negative, very important there. The position of the body at time equals 11 seconds is what? So for our first second, this first second, we have a constant velocity. For the next 10 seconds, we have a constant acceleration. In the negative, it's a negative acceleration. So let's think about this. For the first second, you're driving your car, okay? You're going 24 meters per second. For that first second, a constant speed the whole second. Then you start to negatively accelerate. So that means you're going to start slowing down. Well, what happens if you slow down to a velocity of 0 but continue to negatively accelerate? So you're going and you slow down to 0, but if you continue to negatively accelerate, you're going to start moving backwards. Let's see what this looks like. We need to treat the first second as constant velocity. And we just saw in a previous problem that our constant velocity equation is this one here. How far did they travel in this first second? If they're going a constant velocity of 24 meters per second for 1 second, then they will have gone 24 meters. Pretty simple right there, right? Good for us. Now what about for the next 10 seconds? The next 10 seconds, they've got a constant acceleration. And we want to figure out how far did they go. Any time for acceleration. I'm going to write everything out because you should too, at least for now. Starts out at t equals 1 second. It's already going 24 meters per second. So the initial velocity here is 24 meters per second. We don't know final velocity. We know the acceleration is 6 meters per second per second. This is what we're looking for. How far is that displacement? And from t equals 1 second to t equals 11 seconds, that's going to be a 10-second duration. So we're solving for position here. We want to figure out that position. So I'm going to use this equation here. This is your second equation. Initial velocity of 24 meters per second. Time is 10 seconds. Plus 1/2. Acceleration is 6 meters per second squared. And time is 10 seconds, and we're squaring that time. This is tough. We got x equals 240 here. Meters per, nope, just meters. Ooh, I flubbed up here. What did I do? An acceleration of 6 meters per second squared, but it's in the negative direction. Gotta have that negative there. This should be a negative number. It's tough, you gotta catch that. So this is 240 meters plus 10 squared is 100. 100 times negative 6 is negative 600. Half of that, negative 300 meters. So we end up with a net displacement, 240 meters, plus a negative 300 meters. You're going to get negative 60 meters on that. Alright, so we have negative 60 meters. Negative 60 meters during this 10 seconds. During the first second, it went a positive 24 meters. So to find our net displacement, we just need to add these up. So we have 24 meters plus a negative 60 meters during the next 10 seconds. You end up with negative 36 meters. Does that make sense? Does that make sense that you can have a net displacement of negative 36 meters? Sure, that means that he started out here at a constant velocity for the first second. Then he started to accelerate in the negative, so he slowed down to 0, and then he's made his way back and ended up negative 36 meters from where he started. Not too bad. So guys, this has been the whole kinematics quiz explained. My hope is that if you were struggling with any of these problems and we didn't have time in class to go over them, or you needed to hear it again or see it written out, that this helped you. Remember, we're learning, failing. F-A-I-L, frequent attempts in learning. I'm okay if you fail this because it means you're learning and you're trying, and that's what really matters. Hope this helped. Let me know if you have any more questions or anything, or if I screwed up or goofed up anywhere in here. Well, there were plenty of goof ups, but if any of the math is wrong, any of the physics is wrong, call me out on it, and I'd like to hear that. So have a good one, and I'll be seeing you.